Good evening, everybody. And today we are going to learn a bit about understanding the equipment of esophageal manometry as well as 24-hour pH impedance manometry. So the point that we are trying to do today is just understand the basic, equipment, the process of how do we actually do it, and what are the important points that we need to know before we go on and we actually say that we have done a good job. So understand that a GI lab or a physiology lab is actually the epicenter of your gastroenterology practice. If you look at any gastroenterologist across India or across the world for that matter, uh, GI motility is the most common set of patients that you will encounter in your practice and in your work also. As an endoscopist, you may believe that your predominant work is pancreatobiliary, and there are very exceptionally rare circumstances, I think, except for institutes and larger private tertiary care or quaternary care centers. Usually, you will not have people who predominantly work in pancreatobiliary or third space endoscopy. You will end up working as a gastroenterologist where GI physiology, GI motility comes as a part of your studies. That's why your GI motility lab becomes the epicenter of your practice. It plays multiple roles. You can have a diagnostic role, you can have a therapeutic role. It's part of your daily clinical practice. It's part of your research. It's part of your training to your technicians as well as to your students. And esophageal manometry is one of the essential parts of evaluation of esophageal function. It's part of the esophageal function testing. Similarly, and anorectal manometry is for the rectum. And I think impedance and 24 pH are an important tools that should be in your armamentarium for evaluating GI physiology. Now, the most important thing that I usually tell to all my students and all my fellows is that an accurately done esophageal manometry with correctly aligned equipment will lead to clinical goals. What does it mean? It tells you that to do an accurate esophageal manometry, and for that matter, any manometry, maybe rectal, maybe anything else, you need correctly aligned equipment. And only then you'll actually end up having good clinical goals. So the important point you have to learn is the correctly aligned one. That means that your equipment has to be standardized, calibrated, as per the manufacturer. You have to troubleshoot along the way, and only then you will actually have meaningful test and recordings done. So if you go back to the history of manometry equipment, you can see it used to be very bulky. It used to be a lot of wires around. It used to be limited in its spatial spatial orientations. The used to have very 3 or 4 channels using syringe pumps. Then it developed an Endorpher pump, which increased the channels to 8. Then one of the important points came in 1975 when John Dent from Australia, he developed a sleeve sensor that basically started our journey towards a high resolution manometry. And the sleeve sensor predominantly was positioned across the LES, and that sleeve went on to become a high resolution manometry. And this was finally overtaken by Mu Scientific, who creates catheters today. Finally, we incorporated software algorithms on top of our readings that led to the another landmark event by Dr. Claus, that was the contour plots. Now, what did the contour plots do? It made it very, very easy for understanding how the pressures are changing. We'll talk a bit about it in the subsequent slides. Finally, in 2005, we went on to develop high resolution manometry, and today we are into an era where we have something called as a high definition manometry, where we have gone on to almost 256 sensors. And the most common commercial ones, all which are available, are between 24 to 36 sensors. And we have now some important classification systems coming up, like Chicago classification, as well as the London classification for rectal manometry, which has led to a huge development into manometries. Then finally, we started with conventional manometry where we used to place 4 to 8 pressure sensors across the esophagus, and the spacing was around 5 centimeters. And in the LES, we wanted it to be less than 1 centimeters. And this was basically, the conventional one. It showed different, wave and line diagrams. The problems with conventional manometry was that it was difficult to position the catheter because sometimes you may have a low LES pressure. It was difficult to identify it in a patient who had a hiatus hernia, and that was a problem. And the catheter was simply loop across. In patients who have, where the person who is doing the manometry is not experienced enough, would lead to problems. And if you're in a hurry, you obviously mess up. And this led to a lot of inaccurate diagnosis, and this led to a lot of problems, and one could not measure the whole length of esophagus starting from UES to stomach in single sitting. So the solution that actually came, this was for high resolution manometry, and how did it came into being? That's another story of behind it. So the what we wanted was, we wanted more number of sensors. We wanted it to become a high resolution. So instead of 4, we wanted them to increase to 16, 32, and now 36. And hence, we obviously needed a longer catheter, which where all the sensors could be placed. In a single setting. You could measure from UES to almost the whole of stomach. And but what happens if you actually increase the number of sensors? You can see this diagram. As a lame, as a doctor, you and as somebody who is very intuitive to biology, looking at such kind of waves. So if you look at 5 waves, it's still okay. But on the right side of the image, if you're looking at all this huge number of 36 line diagrams, that's going to mess up your head. It's just something you're not going to understand, and it will take a toll on understanding the physiology. So more channels actually made interpretation much more difficult because it almost was a brain overload. Then finally, what happened to this? So this guy was, brilliant. He thought that when you look into the, topographical maps of surface of Earth, you have mountains, you have lakes, you have oceans, and all these are marked with different colors. Like oceans are blue, and mountains and everything is more in the white. And this goes with the height of the structure. So Dr. Ray Close thought that why don't we do the same with manometry? Why don't we create colors which are aligned with pressures? So what happened was that ultimately you replace these curves with colors using the same topographical maps that we are used to seeing in various Earth surface maps. And finally, this became like this. So it became color. So what it basically meant was that the cooler colors like blue basically meant low pressure, and the darker colors like red or black ultimately became higher pressure. So those difficult and brain overloading line diagrams were eventually changed to beautiful color diagrams that we actually see nowadays. So I think you have to understand the history behind it. Dr. Dent's leaf and the Ray Claw's colors. This simply changed the whole scenario for high resolution manometry. And now I think with more and more 3D reconstruction coming in, we are looking into the future of a high definition manometries. So now what we currently do almost all across India and the world is HRM, that is high resolution. So what is the equipment actually, is needed? What are the various parts of the equipment? So you actually have the catheter or the probe itself. You have a perfusion system if you're using a water perfused equipment, or you have a solid state, processor if you're using a solid state equipment. You will need a recording device which ultimately records the whole reading. And of course, you will need a software and a computer to actually interpret them. So those are the actual equipment that you need. Now, perfusion systems are of various types. Different manufacturers use different perfusion systems. And that is the whole, a problem also, and, in a way, a good thing also. The problem, because if you're using different perfusion systems, you will have difficult time to normalizing the readings across the equipment. Whereas if you use a solid state equipment, it is more or less standardized. That's why Chicago classification for esophageal manometry really harps over using a solid state equipment with impedance recording. But practically, I think across India now and across the world, there are much more number of water perfusion systems than a solid state system. So what I do actually, let's talk of all this equipment one by one. The first equipment is your catheter. So the catheter is, as I told you, can be water perfused or a solid state. So solid means it is solid. It has sensors which are digital sensors. It directly measures the pressure, and this pressure is converted into a digital signals by a computer module. Obviously, this is much more expensive. The sizes are vary between 10 to 16 French in diameter. It's very used. In fact, it is the standard of care for UES manometry and certainly for esophageal body. Whereas the water perfusion ones can vary between 12 to 36 sensors. The flow rate can vary 1.15 ml per minute. They are less expensive to manufacture, but they are more cumbersome to use because you have to attach each and every sensors into its own perfusion system, and there can be an interference at the level of upper sphincter because of the flow of the water if you're using a water perfused catheter. This is how a solid state catheter actually looks like from one of the manufacturers available in the country. Now, different sizes are available for pediatric as well as for adults. It can vary from 1.8 mm to 4.7 mm, and this will obviously change the number of sensors that you are carrying along with the catheter. So this is how the actual water perfusion system looks like. You can have, what it has is it has pressure sensors and it has capillaries. So capillaries are the ones which you can see right now, and these capillaries can actually become very easily blocked, and pressure sensors are actually attached to them, and your water channels inside the catheters can also become blocked, and this is why the problems are in the water perfusion equipment. So you have to make sure each one of these sensors and capillaries are free from any solid particles or air bubbles, and that is why you can't just immediately use them as soon as you join the catheter to them. You have to wait for some time for them to get perfused really nicely so that there are no air bubbles and no solid material running through them. And finally, if you need a computer and a software to read those recordings, and this is how it actually looks like on the screen itself. There are various manufacturers which are available in the country. I think the solid state is available from two manufacturers, the Medtronic as well as by Labori. And the water perfusion system is available from Kangaroo Jeff for the RMH model. You also have Elazar Biomedica, which has a slightly different, connector. Although they have a similar perfusion, but they have a different connector that makes it easy to connect rather than having all the channels connecting together. Have a single connector, and there are different kinds of peristaltic pumps that have actually come out, and I think RMH or Kangaroo Jeff models is also having a newer portable model which has a much smaller peristaltic pump for the equipment. Now, moving on from manometry, we talk of impedance. So what exactly is impedance? Impedance is basically nothing more than the electrical resistance when measured between two sensors using with an alternative current. Now, why do we need, why this physics word in biology? So esophageal impedance monitoring actually detects a reflux, whether it's a acidic reflux, whether it is a basic reflux, whether it is a water, whether it is liquid, gas, what. So all this information actually comes when you add impedance to pH testing. So it can detect all reflux episodes. It is very useful if your patient has symptoms which are with PPIs or off PPIs. You have laryngopharyngeal reflux. A lot of ENT referrals are coming in for these sets of patients. Now, what exactly try to understand it? So air actually has a very high impedance because air does not conduct electricity. You can't get current by just standing in a room full of if there is just air around you, because no ions is there is nothing in the air to conduct that electricity, so you will not feel any electricity. This is why the impedance, that means the resistance to the electricity, is much high. So air should should be considered as something which has a very high impedance. Whereas if you talk of water, water has hydrogen and oxygen and all those ions moving around, and that is why the impedance of water is much more, at the medium level, around 1,000 ohms. Whereas if you have a salty water where you have a lot of water perfusion, happening, that is where you will actually have much. So if you see the salty water, you will see much low impedance, simply because there are a lot of ions to move around. That is why the impedance is around 100 ohms. Now, if we actually are going to see the various impedance values of biological fluids, you will see that the gastric contents is a very low impedance, around 30 to 100. Following, if you talk of normal food products like curd, it's around 400. Drinking water, as I told you, around 1,000. And the esophageal wall itself is around 2,000. Air, of course, is very high. Now, once we have known the basic concept, now what happens in the esophagus? This is a schematic representation of an esophageal wall. And while you are taking a swallow, what happens here is, if you can see clearly, you can see that uh, when a bolus is there, you will see a very nice, air in front of your your bolus. This air is followed by a your bolus of your water. Then there is a peristaltic contraction at this point behind the water bolus, and then finally there is a esophageal wall. And this yellow one is your impedance catheter that is there. So what happens now? Just see here. As soon as you put a catheter in, you will get a baseline recording of somewhere like this, and this is their baseline impedance. Now, when the impedance sensor actually touches the air in front of the bolus, we know that impedance of air is on the higher side. So there will be a bump, a peak, a small hill or a mountain here of impedance because of air. Now, what happens after this? The impedance sensor hits the water bolus, and we all know that the water has a low impedance. So you have this trough, you will have this sudden dip in the impedance. And after that, what happens? The sensor will actually touch the esophageal wall, and you have a pressure contraction happening, and you will have again a gradual increase in the impedance, which actually ends up back towards the baseline. So if you just see the recording, this is how it actually looks like. I will leave it there for you to see again for a proper understanding. uh, as the water bolus or the food bolus moves down the esophageal wall, you will very beautifully see a contraction happening because of the air. You will have an increase in impedance followed by a dip because of water, and then a gradual increase again when the sensor touches the esophageal wall. Now, what are these impedance catheters? Are they different from the esophageal ones? So these ones are the ones, which basically needs a combination of rings. And if they are not closely spaced, they will not send a signal. If the distance between the two sensors is too high, you will not get an impedance signal, because impedance signal is between two sensors. So you have that resistance in between them. So you need more number of sensors here. Now, what are the equipment that we need when we want to test somebody for pH impedance? You combine pH sensors. That is, you can have a 2 pH sensor, or you can have a 3 or 4 pH channels, along with the impedance one. Impedance, you can have 12, 5, 6, depending on different manufacturers. And finally, you have a recorder, something which looks like this. And this recorder basically, goes around, which keeps, recording it. And finally, you will of course need a software to analyze the equipment, the recording that you finally get. If I just have to go ahead, I think this is the other common impedance manufacturer catheters that are available. They are antimony based. They have an internal reference, and finally, we have to standardize them. You can also combine HRM with impedance. The impedance data will give information about the location of the bolus and the air in the esophagus, and we can actually measure using metal rings to a manometry catheter. So this is how it actually looks like to combine a manometry catheter with an impedance channel. So this is how it looks like when you combine on the software itself. This pink part is basically is what the impedance thing, and the normal manometry looks like this. In this patient, you can see a reflux. This is the gastric content. There's an increase in gastric pressure here, and the gastric content is going into the esophagus, into the mouth, and the patient is regurgitating it into and then swallowing back as a swallow. So this is a swallows happening to the reflux. And finally, if it happens versus a closed UES, you will have a pressurization, and if it when the UES opens up, you will have a belching. So this is how it looks like if in a patient who is post in Nissen's fundoplication and complains of gurgles in chest. This is how it's happening. You can have a bolus pressurization around this area. You have a break in the peristalsis, a retrograde movement, and finally increased pressure and gurgling around this area. So to conclude, I think the most important thing for us to understand is that the GI motility and a physiology lab is essential part of your, endoscopy suite. In fact, it's a most essential part in my opinion. You have to know your catheters, you have to know your equipment, and it is much more important to understand how to troubleshoot it more than interpretation. It is how you actually do the test that is much more important. If you are not doing the test well, you will not find anything at all. And manometry, pH, impedance, and its various combinations are available, and you should be familiar with all this equipment. A very correctly done manometry is essential if you really want to have a correct interpretation. So my request to all of you is please make sure you are uh, before you test, you make sure your equipment is calibrated well. I have just covered the equipment part of it. I have not covered the calibration part. I have not yet covered the troubleshooting part. I have not yet, covered the interpretation part. I think we'll take this into as a four-part series where we will learn of all these things. But to begin with, I think knowing the equipment is the most important thing. So thank you again for being with us, and I hope this is useful for you.